Okay, looking at average rate of change in calculus. And with average rate of change, and anytime you see the word rate of change, you really just need to think of slope. The phrase rate of change is a reference to slope, always, and how we get the slope may change, but if it's an average rate of change, then we're just doing old-fashioned algebra 1 slope, and so it means find the slope of the secant. And so here, first question is asking to find the average rate of change of that function on the interval 1 to 4, and I'm just going to show you the work for these because it's basically ninth grade level work here, but the average rate of change is change in y over change in x. And so you would get that by finding the y coordinates, f of 4, and f of 1, and subtracting them by the difference in the x coordinates of 4 and 1. And here is the answer for that one. So plug in 4, plug in 1, find the y, subtract them, and get your slope. So my slope is 2. That is your average rate of change of this function from 1 to 4. Same thing, even if it's ugly and trigonometric, you still will find the y coordinates, in this case at pi over 6 and pi over 2, subtract those, and then divide that by the difference in the x coordinates. And so you would end up with something like this. So f of pi over 2 minus f of pi over 6 over pi over 2 minus pi over 6. And again, a little reminder from ninth grade. It doesn't matter which one you start with. If you want to start with pi over 6, that's fine. On top, just make sure you also start with pi over 6 on bottom. So whichever x coordinate you use for the beginning of the numerator, make sure you use that for the beginning of the denominator. So there's average rate of change. It's a fancy way of saying find the slope. And so here is your formula for average rate of change. That is f of b minus f of a over b minus a. That is nothing new. That is something you have seen. However, the word or the phrase I'm about to give you right now might be something new. That is lovingly referred to as a difference quotient. A lot of things in math have really weird names that don't make sense, or they're named after people that don't tell you much about what they do, like Pythagorean theorem. The word Pythagorean doesn't mean triangle. It's the name of a person or named after a person. But difference quotient is not one of those phrases because this is literally a quotient of differences. So I like that name. It tells you exactly what this fraction is. And the difference quotient is the formula for slope. And slope is the core for all things in calculus. So let's move on and add a little bit of context to the slope. Let me move my head out of the way or make it smaller. It's a big old head. Fine, I'll use my mouse. So there we go. A lot of times slope and rate of change is tied to motion, where we are looking at position, velocity, and acceleration. So if you've taken physics, you should know the relationship among those three. But in calculus, we'll be using derivatives eventually to discuss this relationship. But do remember that velocity is the slope of position and acceleration is the slope of velocity. And the way you get that slope may change, but that relationship is always true. So anytime you're looking for velocity, think slope of position. Anytime you're looking for acceleration, think slope of velocity. And you do need to know how to measure the units. Velocity is like feet per second. Acceleration introduces a new unit of time. That'd be feet per second squared. There is something called the jerk, which is feet per second cubed. And then after that comes snap, the crackle, the pop, and they actually name them quite a ways down the line. But we're going to be looking at position, velocity, and acceleration. So looking at number 3 here, find the average velocity of an object in motion over the interval 0 to 2 if its position is given by this function, and s is very frequently used to describe position. So there's our position function, and then I was just say use feet and seconds for units. And so we want the average velocity, and we have position over an interval. Velocity is the slope of position, so we're going to do the exact same thing we were just doing. It's f of b minus f of a over b minus a, and we're using position here. So s of 2 minus s of 0 over 2 minus 0. And this one actually does something interesting because s of 2 and s of 0 are the same. We are starting and ending at the same spot, which results in an average velocity of 0. Does not mean you didn't move anywhere. It just means you ended up where you started. And your average velocity is 0 feet. And I don't know why I put a square on that foot unit or time unit. Let's get rid of that. Okay, so there's average velocity given the position. And then you can also ask for the average acceleration if you are given velocity. And so again, the relationship from acceleration to velocity is that acceleration is the slope of velocity. So this is just asking, Here's a velocity on the interval 1 to 4. Find the slope of velocity. So we'll use the exact same difference quotient, v of 4 minus v of 1 over 4 minus 1. Work that out, and in this case, you get -3, and the units for acceleration are feet per second squared, and you do need to know that, and I do expect correct units to be attached to your questions or to your answers. All right, now I'm going to talk very briefly about instantaneous rate of change, really just to give you a preview of the future. We are not ready for instantaneous rate of change, but when we get there, do know that rate of change still means slope. We are still going to find the slope, but this time we are finding slope at a single point. What is the, one question could be the velocity at time equals 6. Well, if you only have one time value, you can't do a measurable change in y over change in x. And in these cases, we're going to find the slope at a single point by finding the slope of the tangent, which is found with the derivative. And so we haven't talked about derivatives in my class yet, but when we get to instantaneous rate of change, we will use derivatives. We will not use change in y over change in x, and I'm not going to answer these two questions. But it is still a measure of slope. It still measures slope. It's just not with the old-fashioned Algebra 1 method. All right, so let's look at another way questions can be asked, and that can be asked, or they can be asked with information presented as a table of values. So right here, we have the position of something moving at 5-second intervals. So we have time going from 0 to 25, and then we just have various positions as it goes along the way. So after 5 seconds, it traveled 5 feet all the way to 25 seconds later. I'm sorry, after 0 seconds, it started at 5 feet. And 25 seconds later, we are at 42 feet, and you can read all the numbers in between. And question 7 says, find the average velocity over the interval 5 to 20. Well, that's not too bad. 5 is here, 20 is here. And if I'm going to find the average velocity over that interval, we're going to do old-fashioned change in y over change in x. So my position measurements are 32 and 12. My time values are 20 and 5. And we'll just subtract those. 32 minus 12 is 20. 20 minus 5 is 15. And that would reduce to 4/3. And units, on top, I subtracted feet. On bottom, I subtracted seconds. And there's your answer, 4/3 feet per second. And in these problems, I do want you to write the difference quotient. Start with the difference quotient. Include that difference quotient. And I want you to get in that habit, because on the AP exam, if this is free response, they very likely will reduce points if you start with 20 over 15. They want to see that difference quotient. So include the difference quotient every time. Start by writing that. Then if you want to jump straight to the simplified version of 4/3, you can. You don't have to march through 20 over 15. We'll do the same thing here. Average velocity over the interval 0 to 25. So 0, that's the whole interval, 0 to 25. And do write that difference quotient, 42 minus 5 over 25. And I know it looks stupid, but it's not a difference quotient if you are not subtracting in the denominator also. So you need to write 25 minus 0. And that ends up being 37 over 25, which does not reduce. Units are still feet per second. So there we go on 7 and 8. And then finally, the last two ask you to estimate the velocity at a single point. We want the velocity at 7. This is not an average velocity. They want us to estimate the actual velocity at 7. And 7 does fall right here between the 5 and the 10. Now, on these types of problems, you have to use information that's in the table. You cannot try to extrapolate between these values and estimate, okay, well, maybe that's a 15 between the 12 and the 18. You can't do that. You have to use information that's actually on the table. And so what I like to do, and on number 9, we don't have any options, but for this one, since 7 is between, I don't know why I erased the 7, since 7 is between the 5 and the 10, to estimate the velocity at 7, we're actually going to find the slope from 5 to 10. And so my velocity at 7 is going to be approximately 18 minus 12 over 10 minus 5, which would be 6 over 5. So the way this is giving you a decent approximation, If we think about this graphically, I'm just going to draw some kind of a crap graph right there. And let's say I want the instantaneous, I want the slope at that point, that red dot I just put there, which is kind of like what I'm doing here. I want the slope at 7, and the slope at a single point is modeled by the slope of that tangent. And right now, or with the table of values, we cannot get the slope of the tangent exactly. So what we do is instead of finding the slope at that point, we go just a little bit to one side, and we go just a little bit to the other side, and we are finding the slope of the line that connects those 2 points. So if I find the slope of the line that connects those 2 points, as long as you stay as close as possible to the point in question, the slope of that green secant, as we sandwich to the point in question, is pretty close to the slope of the tangent. And so that's what we're doing here. If I want the slope at 7, I can't do that with the information given. So the best I can do is find the slope between 2 points that are around the value of 7. And so we have something similar on number 10, on number 10 here, except this time they want you to estimate the slope at 10, which is on the table. The fact that the point 10, 18 is on the table does not change my approach at all. I still prefer to pick a point just to the left and a point just to the right and sandwich the one in question. And so I would say the velocity at 10 is approximately 23 minus 12 over 15 minus 5, which ends up being, 11 over 10? And that would be measured in feet per second. So there's your estimate at 10. Now, if your point actually is on the table and you're asked a question like this, other acceptable answers are to do the slope from 5 to 10 or the slope from 10 to 15. So you could also have done the position, I'll say S of 10 minus S of 5 over 10 minus 5. Or we could have done the position at 15 minus the position at 10 over 15 minus 10. And when this has shown up on the AP exam in the past, they accepted all 3 answers. However, my preference is to go on each side and sandwich that point. It's just the way I prefer to do it. So I'm going to label position as S, and there I'm done. I'm through talking.